And this is part 2 of the chapter on maxima and minima, 14.1. Okay, today we're going to cover the second derivative test. So what we have learned earlier is how to use first derivative test. You look for the values slightly to the left or to the right to sketch the graph and see how the shape of that point looks like, so that you can actually get a sense of whether it's a maximum or minimum point. Today we'll learn yet another method, okay, called the second derivative test. First and foremost, let's look at the notations. Okay, what is a notation? What's the notation here? For example, if you start with a function y is equals to x cubed, if I were to differentiate it with respect to x, okay, you get 3x squared. Now, if I differentiate one more time, okay, what I get is something called the second derivative. So what I get here is 6x. Similarly, if we are given the function in terms of x is equals to x cubed, the first derivative, you put one dash there, you get 3x squared. Second derivative will be, the notation will be this. You notice that there are two, okay, over here, and this will be equals to 6x. Alright, so now we are aware of the notation of what we need to write down when we differentiate a function twice. How is this second derivative test actually used? It goes like this. So this one, you just have to remember this, that when the second derivative, okay, you sub in the value of x at the maximum or minimum point. If the value is less than 0, it's a maximum point. When the second differential, you sub in the x value of the stationary or turning point, and it's greater than 0, it's a minimum point. How I actually remember this is that it's reversed. What do you mean by reverse? Less than 0, then it's maximum. Greater than 0, the reverse, it is a minimum point. Okay, that's how I memorized it. I will now present to you example 4. So example 4, what we are given here is this. So first and foremost, in example 4, what they want us to do is to find dy dx. Very clearly, this is u and this is v. U times v, what we need to apply is the product rule itself. So now, what we do, dy dx. So what I get is v multiplied to du dx, which is actually 1, then plus u, then dv dx. So I differentiate square root of x plus 2. So it's half x plus 2 minus half times 1. So if I simplify this, what I get will be x over 2 square root of x plus 2. Okay, now next thing is this. For this question, I know I always say that we do not need to simplify, but I think, right, for purposes today, what we can do is, since we're going to do the second derivative test, I think it will be good for us to simplify. So what I will be doing here is I multiply, the lowest common denominator is 2 square root x plus 2. So here I'll multiply by 2 over 2 square root x plus 2, 2 square root x plus 2 to get my lowest common denominator. So if you simplify everything, what you get is 3x plus 4 divided by 2 square root of x plus 2. So that is dy dx. Now, part 2, explain why the curve has only one stationary point and determine the nature of the stationary point. Okay, so first and foremost, in order for me, okay, to determine the stationary point itself, so what I'll do here is this. Now, for stationary point, if you recall, dy dx is equals to 0. So if I solve very quickly, my x value is negative 1 and 1/3. Okay, so in order for me to prove that there's only, notice that in this case when I solve, right, there's only one value of x. Okay, so in this case, this is the only solution. By solving, I say that x, right, this is clearly the only solution, okay, for dy dx is equals to 0. Okay, so hence, okay, there is only one solution. Okay, now in order for us, okay, just recall what our dy dx was. So dy dx was this 3x plus 4 to root x plus 2. Let me just give it a copy here. Okay, now okay, and remember that our stationary point occurs when x is -1 and 1/3. So what I will need to do now is to actually be able to find, okay, the nature of this point. So either we can use a first derivative test, but since we have just learned the second derivative test, so why not we try it out? Okay, so if I differentiate one more time, now what I need to do is to apply the quotient rule itself. So if I apply the quotient rule, okay, what we get is v du dx plus u dv dx over v squared. So what we get is v, okay, times du dx plus u times dv dx. So in this case, what I get when you differentiate this, what I get is 2 over v squared. Okay, v squared will be 2 square root x plus 2 squared. So then if I will just skip a few steps here, okay, I won't go through the mechanics of this. Maybe I should, okay. I'll just simplify. Okay, then in order for me to simplify the numerator, I multiply this term by root x plus 2 over root x plus 2. This term, root x plus 2 over root x plus 2. By doing so, what I can do is to resolve this square root of root x plus 2 in the denominator of the numerator. So what happens here will be this, okay, so I will get, okay, or the other way around, sorry, is I can actually multiply, okay, sorry, that's not a very good way. I think a more intelligent way is for me to multiply root x plus 2 and root x plus 2 to both the numerator and the denominator in this case. So if I were to do this, what I'll get is 6x plus 2 plus 3x plus 4 divided by 2 root x plus 2 square times root x plus 2. So if I simplify everything, what I'll get is 9x plus 16 over 4, then x plus 2 to the power of 3 over 2. Okay, so this, right, will give me the second differential. So now when x equals to -4 over 3, my second differential, I will substitute in the value of this into here and here. So you press your calculator, you should get a value that is positive. So I can actually not calculate the value and just write it down, okay, and you'll find that this value is actually positive. So if the second differential is greater than 0, then this implies that this is a minimum point. Okay, that is it for example 4. So now, okay, why don't we pause the video for a moment and try 4. Notice for try 4, what they have actually asked is for you to actually use the second derivative test to determine the nature of the stationary point itself. So do pause the video and try this out, and I will carry on, okay, with the solution in 3, 2, 1. Okay, let's go. Okay, so the first part should be simple enough for you. If you have the curve, you differentiate one time, you let the first differential be equals to 0, you can find the x value of the stationary point. Substituting the x value of the stationary point into the original equation gives you the y value, and hence the curve has a stationary point at 4 and -5. Then, okay, if you do the second differential, okay, they didn't show you this second differential. So the second differential, yes, they did, okay. If you differentiate the first differential one time, you get equals to 4. In this case, you don't even need to substitute the value of x. Immediately, you notice that the value, right, is just positive. You don't even need the x value of 4. So if it's positive, remember it's the opposite. So positive, it is a minimum point. So by the second derivative test, 4 -5 is a minimum point. Okay, now we move on to example 5. I believe that this is the last example for this chapter. So now, there's the equation of a curve is given by this. Find the value of x for which the curve has a stationary point. Okay, we've done this up 10 times, so I'll just go quickly here. I differentiate. So I get 6x squared minus 12x plus 6. So at stationary point, okay, my gradient is equals to 0. So 6x squared minus 12x plus 6 is equals to 0. So the making your life easier, dividing everything by 6, okay, we get this. Okay, then now we get x minus 1 squared is equals to 0. So therefore, okay, at x equals to 1, okay, is a stationary point. Okay, now what I want to do is, okay, find the coordinates of the stationary point in part 2. So I need to substitute it into my original equation. Okay, so now for x equals to 1, this is my equation here. So y is equals to 2. And hence my y value itself will give me -3. Now, by applying my second differential, okay, my first differential was here. So now I will apply my second differential, since this is what we learned. If you use the first derivative test, it will work just as well. So now, for my second differential, we get 12x minus 12. Okay, here is where something special occurs. Okay, if you notice, my x value was equals to 1. So if I were to substitute this into my second differential, I get 12 times 1 minus 12 equals to 0. Oh no. Okay, why oh no? So what we have already learned so far is that when my second differential my second differential is less than 0, is the maximum point. If my second differential is greater than 0, is the minimum point. But there is no mention of what happens, right, when my second differential goes to 0. Okay, one of the wrong concepts that people will say is that, oh, it's equal to 0, it's neither maximum nor minimum, so it's a point of inflection. Okay, that is incorrect. All right, so when it is equals to 0, it means that, right, the second derivative test is inconclusive. So we cannot use the second derivative test to determine the nature of this stationary point. So what do? Okay, we need to go back to first principles again. We need to go back to our first derivative test. So back to my first derivative test. So again, just to repeat, if the second derivative test fails, what we need to do is to go back to our first derivative test. So let me quickly set it up. And also I show you what I mean by you need to actually sketch the diagram, okay, to apply the first derivative test. So what we have is this. Okay, so the x value, if you remember, is 1. So my x value 1, then 1 plus 1 minus, slightly to the right of 1, to the left of 1. So what I need is the dy dx sine, okay, then how does the tangent look like, and how does the sketch of the curve look like. So if you substitute it in, okay, 1 plus, let's say use 1.1, you substitute into here and here, you will find that this is a positive value. Similarly, okay, if you substitute in a value say to the left of 1, maybe 0.9 to here and here, you find that it's also a positive value. So my tangent is this, 0 and this. So okay, I made a small error here. Okay, oops. The sketch of my curve in this case will actually show that it's a point of inflection. It just happens to be a point of inflection. Okay, so hence, okay, 1, -3 is a point of inflection. So to repeat again, when my second derivative test spits out a 0, so to speak, the second derivative test is inconclusive. What we need to do is go back to the first derivative test to see or to determine the nature of the stationary point. Okay, now please pause the video and try 5, alright? And then I will go through try 5 with you in 3, 2, 1. Okay, same thing. If this, we start with y equals to 6x to the power of 5, you differentiate once, you get 30x to the power of 4. So once again, rinse and repeat. When dy dx equals to 0, you get stationary point. You solve x equals to 0. You take x equals to 0, you put back into the original equation, you get y equals to 0. Hence, the stationary point is at 0, 0. We try to use the second derivative test like this. You notice that when x equals to 0, then the second derivative will give you a value of 0 as well. So now, okay, once that occurs, once again, we are unable to determine the nature of the point. So what we need to do is to use the first derivative test. So by putting in the value of x equals to 0 and using the first derivative test down here, okay, what we will get is this table, which I will not go through in detail. We've gone through this, and this point just happens to be a point of inflection again. Okay, so I must repeat myself. I know I said this a few times during this video. So when the second derivative test is equal to 0, the test is inconclusive. It does not, okay, does not mean there's a point of inflection. It just is inconclusive. So we need to use the first derivative test to determine the nature of the point. So it just happens that the example as well as this try 5 will give you a point of inflection, but you will actually do need to use the first derivative test when the second derivative test fails to actually determine the nature of the stationary point. And this is it for 14.1, and thank you for watching.